Okay.
That's it.
That's it? Good. It's gone. So I'm going to present you the first technical part of how we actually get the data out of the detector. And then what we do what we have to do to get the data onto mass storage, to give it actually to all these fantastic analysis chain which you have been hearing about, and also a little bit about the future. Now, this is to some extent a big data challenge, really in the sense of raw amounts of bits and bytes. So it's very different from multivariate analysis, but there's a few interesting challenges here as well. So this is the Large Hadron Collider. I mean, a nice graphical picture. There's the 4 experiments, not to scale. I've deliberately made the LHCb a bit larger than it is in comparison to the others. So, but just to say that what is happening, what I'm going to present you, is happening 4 times, roughly. But actually, there's a few small experiments which we normally just don't talk about. Okay, so in general, Mitesh has explained to you that what we are looking for is rare. So these things, the interesting things are normally rare. For all the not so rare things, the Nobel Prizes have already been given out. And so you need a machine with a lot of collisions. These colliders and the detectors which are associated produce signals which have to be acquired by normally fast electronics. And this produces a lot of data. It's where I will try to convince you about this challenge, which means that you need a data acquisition system. So you need a system to get all this data securely, and then you have to, then of course we can't afford to store all this data, so we have to filter them somehow, and this was mentioned by Mitesh in his first presentation. This is this trigger system he mentioned, the high-level trigger. And then the rest has to be stored. So I'm going to show you a little bit, a few parts of this chain here. So why is this a challenge? So this is a nice plot from another experiment, CMS. Why is the data acquisition a challenge? So if you think in CMS, for example, but it's not, the numbers are a bit different for other experiments, but similar. If you count all the channels, so the individual sensors in an experiment, in the detector, these are about 15 million. There are 15 million detector channels. Typically, detector channel is value of 1 byte. Depends a little bit, the ADCs are sometimes 2 bits, sometimes 12 bits, but the average says 1 byte. Now you read this out at 40 megahertz, so every 25 nanoseconds you get 1 byte from each of these 50 million detector channels. This gives you a raw data rate out of the experiments of 600 terabytes per second. So this is a lot of data. I mean, even with modern technology, this is a lot of data. So clearly this is a bit, and for LHCb, for all these experiments, the numbers are in the same order of magnitude. So how do we do that? So how can we feed this? Now, the first question we should ask ourselves, and I think it has been answered already, is, I mean, is it even worth looking at all this data? I mean, is all this stuff interesting? And the answer is clearly, if it's asked like that, is not. No. So you see here, this is sort of the plot of interest. So you see here the center, the mass energy of an interesting object out of these events. And oops, and this was too quick. The main point is, as usual, in red. The really interesting, juicy stuff is happening very rarely. So typically 100 GeV Higgs will happen out of the 40 million collisions per second. You will have only in 10 out of these collisions, so every 10 seconds you will have actually a Higgs boson. This just means that it's produced. It does not mean that you actually capture it in your detector reliably. So that you lose another order of magnitude by inefficiencies of detectors and stuff like that. And as Mitesh has also shown you, the heavier these guys get, the statistically more unlikely it gets that you produce them. So this, you have to fish out from all this other stuff here, which is not so interesting. You have to fish this out somehow. So how do we do that? So just to illustrate this is another nice plot which shows nicely what is the challenge in the trigger. So this is what is happening in, I think, well, others will see. Anyhow, this is when you have several, this is when you have protons colliding at 14 terabytes. This is simulation, no? But we are not yet there, but almost, and it looks the same actually graphically at 8 TeV. This is when protons collide at the LHC. And this is what you always get. This is the background noise, the music, so to speak. The background. And what you're looking for is this. So that would be this. I hope we will get a few tomorrow. This would be a gold-plated Higgs candidate into 4 muons. This is the easiest. The others are more complex. And it's impressive that people actually work also with the more complex ones. So this is somewhere in here. Now the problem is that this is, as Philippe said, is every 10 seconds you have one of those, and this you get 40 million times per second. So now you have to dig it out. This is the problem. Okay, now just backtracking this, I give a lecture about data acquisition often to students, and so you forgive me that I know you're a lot of experts here, but I can show you a very simple graph of what data acquisition with a trigger actually means. Because conceptually, even though the systems are super expensive, very large, and require an ungodly amount of people to operate, essentially this is what we are doing. So you have a sensor, or many sensors, it doesn't really matter, and now the processing, so this would be this boosted decision tree or whatever, this, you cannot afford, at least currently, to do the full processing you would like to do on every sensor at every interaction. This simply, the electronics is too expensive and or too complex, so you can't do that. So what you do is you fan out the data directly after the sensor, and you put them through some kind of simplifying electronics logic, which you call a trigger. So obviously this must be a little bit less complex than this, otherwise you don't gain. And you back off this system here, which would feed this for the time while you're doing that. And then only in a certain fraction of the cases, you actually tell this guy, okay, this was interesting. So yes, you fire the trigger. This was interesting, and then we pass it on to the processing stage. And then in the processing stage, we also call this trigger, even though this is technically speaking not really a trigger, it's rather a filter. So we do a selection here of the interesting events and then go on. So this is what this trigger data acquisition is about. Now, in reality, it looks more complex. I show you here an example of the real trigger system of LHCb. This is our vertex detector, the detector which is just around the beam pipe. So you see here the small cutout. This is where the beam goes through. So there's a hole. Otherwise, there would be a hole if the detector were closer. So this is actually a very fancy detector. We can retract it in order to and put it back, and all this with micrometer precision in order to protect it from the beam when the beam is injected. So, and here, what we are trying to do here we try to find these interaction vertices. We try to find out the number of primary hard collisions where proton has met proton in real time. This we do here by a clever mapping of the geometry. We do a kind of online histogramming of the so the detector geometry is actually made for this. So it gives us the R coordinates of the tracks. We do a reconstruction of these tracks. We project them onto the beam axis, and then we see how many. And then we do a histogramming of these intersection points, and we see how many intersections we get. And from this we can do a counting and get the number of primary interactions. And then we can decide, do we want this or do we want this not? And we do this in 2 microseconds. Okay. So that's why it's challenging to do this in standard software. I mean, if you think of the time it would take to take the data out, just move it over PCI Express into a GPU or something, do the processing, and send the result back, 2 microseconds is not a lot. That's why this is currently the domain of FPGAs and custom-made electronics. So there's an algorithm here which is not overly complex. I'm not going through this just thing. So, but that's typically, we do this also for calorimeter data, for muon detector data. But obviously, this short time and the fact that it's implemented in FPGAs has limitations. We lose here. So there's losses in we lose interesting physics, which if we had more time or if we had more data at our disposition, we could do better here. Okay. Now, after we have done the triggering, we have really to get the stuff out now, out of the detector into computers. So these are a few of the DAQ design guidelines. Okay, nowadays you do everything with, you try to do everything with commercial systems. These are large systems. You need intelligent control. And of course, you want to operate them at high efficiency. Since this is all publicly funded, you would like ideally that it doesn't cost anything. So you use cheap technology, Ethernet mostly, and PCs. Yes, we use Ethernet, so I mean, I had to show this here. For those, some of you certainly work also on systems, no? Yes, so Ethernet is nice because it's cheap, and it's cheap, and it's cheap, and yes, and it's cheap. And, but it has also disadvantages. No? It's easy to understand. I mean, the Berkeley socket stack is certainly something which is easy to grasp. Those of you who have tried to program InfiniBand with the OFET, I mean, will know what I'm talking about. So certainly this is nice. But it has disadvantages. For example, and one of the main disadvantages is that in Ethernet it's perfectly fine to drop frames. So that this is sort of left to higher level protocols to deal with that. That's not so nice if you have, I will explain why this is a problem for us. Okay, so this is how a typical data acquisition, so this is LHCb's data acquisition system, but trust me, the others look similar. Here we have the LHCb experiment. So you have data links, custom data links from the detector feeding out in some kind of adapter boards. which do a protocol conversion. Here you need to run some kind of custom protocol because you're in a radiation area, and you can't run standard Ethernet here. You have also strong magnetic field, and so there are many reasons why you need some kind of custom protocol. Now, in order to feed this into a standard network, you have to convert it to Ethernet, and while you are at it with these FPGAs, you do some pre-processing on this data. And then you feed it through a network of core routers, and then into edge switches, and then in a server farm for filtering where all these magic algorithms run, which we have heard about. These boxes are big. I show them because they are big because they are expensive. This is about 5% of the total cost of our experiment. It's just in these routers. And the reason for that, why we need so expensive stuff here is this mostly. This is again a cartoon, but it shows an important truth. So this is the congestion problem in switching networks in general. So you know all this. So typically in data acquisition, of course, the collider is like a clocked source. No? It makes really every 25 nanoseconds it makes boom. Actually, only 50 currently, but okay, fine. Anyhow, and the data arrive at the same time in these converter boards, and they will now all want to go to the same PC because there in the PC you want to get the data together. You want to look at them. Now that means that in the switch they arrive all at the same output port at the same time. And then it makes bang. And standard Ethernet behavior, if there's too much overcommitment, this is just packet drop. Huh? So this is fine. And this is really a problem in general in these data acquisition systems because the sources are synchronized, because the original data source, the accelerator itself, is synchronized, because the beams are made by an AC frequency. So there are two ways to work around this. Either this guy can buffer a lot, which makes him expensive, or you have some kind of protocol traffic shaping to work around this. I just show you here one quick animation. I mean, we don't want to, I don't know how I'm doing with time. Probably not well, no? Okay, I will hurry up, sorry. Okay. Yes, so this is what we are typically doing. So we have some kind of traffic shaping where we have an event manager, data come in from the detector, okay. Then they go out. Now you see they are buffered in the switch. PowerPoint is nice, isn't it? And then they go out to this guy. In the meantime, already next stuff is beginning. So of course, the cumulative buffer, depending on the data size here, the cumulative buffer in the switch has to be fairly class devices, which is a pity because these telecom class devices can do a lot of stuff which we don't need. Actually, the only thing we want from this device is the buffer, and it can do OSPF and all this kind of stuff, which is completely unnecessary because the network is completely static. That's a little bit a mismatch, no? But okay. So here, clearly, to doing something more clever on the networking stack could help a lot. I mean, for future generations of doing these kind of experiments. Right, okay, I'm not going to, since you're all. This one, okay, this is just a variant of the same thing. Now I will fast forward to not, okay, yeah. So right. Okay. This is just a different picture of the same thing, a little bit more generic. So this is now the real numbers which we have. So in LHCb we transport actually 55 gigabytes per second. So remember this terabyte per second. So this trigger system here, which looks in real time in a few microseconds at the data, it takes actually the task to reduce the data from about the terabyte, 2 terabyte per second to this 55 gigabyte per second, which we actually now push for the network, and then to this server farm. Here we have currently, it's not nearly as large as yours. We have something like 1,700 servers, but we keep adding. So whenever somebody has a new clever idea, new servers have to be added. And then we accept data at about 4 to 5 kilohertz. This is also a number which keeps growing, to the pleasure of our friends who are at the other end of the pipe. This is the number at which we put out. No? If you ask our analysis friends, they would rather shift it towards the 1 megahertz. I mean, just to have it on tape. No? It's always better to be sure. Obviously, this data needs to be monitored online. It's an interesting task because you have to have some kind of real-time feedback, because here you get just bits and bytes in. It doesn't tell you that the detector is actually fine. No? I mean, it can be that all voltages and stuff are up, but you have to have some real-time feedback on the real physics quantities to be sure that the data is actually, that this actually makes sense to store this data, that you don't have to do. So this is an important aspect here where fast feedback is needed and where clever algorithms have to do what normally human people would be doing to assess the quality of the data. And this is an area where work is certainly also needed. Yeah, these are some technicalities. If later in the discussion somebody wants to ask me about what I'm spending my day, these are some technicalities about data acquisition. I'm not going through this here now. This is just for the conoscenti, those of you who like network protocols. This is a bit a comparison of the 4 LHC experiments, what they're using, what the average link load is. You see, we are running the networks normally at a rather high link load, which makes us more vulnerable to fluctuations, but of course it's a cost reason as usual. We are using, and so these are the protocols which we are using for this. Some people have started looking at other network technologies, namely InfiniBand, and this is quite interesting when you see how this is developing. Yeah, this is some kind of figure of merits. So what is pushed through the and you see that, so typically we are storing between a gigabyte to 4 gigabytes per second, and these are the sizes of the events and the rates. For ALICE, the heavy ion experiment is a bit different than for the others because they are using lead-lead. So in lead-lead you get many more data per collision, but at a lower rate. There they find the quark gluon plasma, maybe. Yeah, so the high-level trigger farms. Now, the algorithms which are running in the high-level trigger farms, Mitesh has presented to some extent. I'm just showing you here that we invest a lot of computing power on that stuff. And we have all the fun which comes with so many computers, managing them, and keeping them in order and stuff like that. These are reasonably large farms, and they are really single-purpose. They do nothing else. So this has advantages and disadvantages. And counting, we are constantly adding. I want to just show you a little bit what is the future of the LHC. So we are now approaching what is called in the LHC lingo the long shutdown 1, LS1, where we will shut down the accelerator for 1.5 years to do major overhauls, in particular to ready the accelerator for the full energy, 14 tera electron volts. And we will take advantage of that to do some consolidation work. Then there will be another 3 years of running, and then in 2018 there will be another full shutdown of the accelerator, where they will increase the number of collisions per second in the accelerator. And there, LHCb, my experiment, and those other experiments wants to do a major overhaul. So we want to completely redo everything. Well, not quite, but almost. And so this is what we are now working when we are not running operations now. This is what we're spending our time now, is working on the upgrade of this stuff. The reason of this is that currently, as I explained, in this hardware trigger, in this system which does this 2 microsecond decision, we lose quite a bit. So it's a pity, actually. And so the idea was to abolish this and to do everything in software. So now really read everything out in the network, read everything out to computers, hoping that Moore's law will help you and the networks will be fast enough. Okay. It's challenging, but we think we can do it. Yes, so this looks then like this. So before you had here this kind of mechanism which magically tells you which ones are interesting, and now you just push them through. That means that you have to do some kind of intelligent compression directly after the sensor has been acquired. Otherwise, it would simply be too much, and then you feed it out so to multiple instances of this network. Okay. One interesting question will be the network technology, InfiniBand, or some version of Ethernet. So this is currently being studied. The network which is required is a 32 terabit per second network. You can almost buy that today. I mean, for certain you can buy it. I mean, the question is if you can afford it. But even when you I've talked to Mellanox and all these network manufacturers, they always take a step back when you tell them that you really want to run this in one single system. So it's still not, I mean, it's certainly possible, but needs some thinking. There's a lot of links here. Yes, this is some explanation of these are the figures of merit here. Here we will increase the output rate to 20 to 30 kilohertz. Not completely clear why, because, okay, anyhow, we will increase it a lot. And this is how it will look like. So we will have some kind of 10,000 custom links from the detector, and then feed this into some kind of converter units, then have this network here, and then we will have a computing farm somewhere, where these compute units, this is now not completely clear. Currently, these are just conventional AMD Intel CPUs. In the future, this could be something supercharged with GPUs or something. This is not so clear. People are starting to look in it, and maybe this can help us to make this cheaper. Currently, we have estimated we need something like 5,000 servers, but it would be actually more interesting and more intelligent to do something more clever than just do more of the same. So we'll see. So the readout unit obviously is this kind of protocol conversion unit which I've presented to you. It will need some kind of FPGA, you need some kind of programmable electronics to do this streaming data conversion. So, but how you fuse the FPGA with a custom CPU, there are interesting ideas. For example, one could, for example, implement the FPGA directly on a standard Intel socket, so that used in the QPI interface. It's more a question how you get the data into the PC. But this is an interesting field of R&D right now. And then you have to send it out over some standard network protocol. And then in the compute unit, in the end, you have to assemble all these fragments. You have to bring them together, and then you have to run them through these filter algorithms. And also this you have to do ideally in a clever way. One example, people are studying currently if one could take a data directly from the network into a GPU, do a first level selection, and only the interesting data are sort of put into main memory to save main memory and to speed up the computation. Yeah, so here's some final words about this. I didn't talk about DCB because so far our experiences were quite disappointing, but okay. Right. Yes, obviously network topologies. This is another thing we are studying right now. Simulation there is very important. Clearly it would be nice if one could replace all these core routers by some kind of fat tree topology of simple switches, which could make the system more interesting to manage, but potentially a bit cheaper also. So this is something where I'm currently working on with students to see if one can do this like this. That if somebody has experience with this kind of topologies, I'd be very interested. In supercomputer centers, they tell me that normally they still put large director routers in the middle because it's easier. But okay, we'll see. Okay, right. So, in summary, I mean, the main problem in data acquisition is not so much as I listed here is if you can do this somehow to transport this data. It's more if you can do it in a clever way that you can actually afford it. And what is currently being studied is how to work around this problem of the burstiness of the traffic. How you can get the data from the front-end boards into the host CPUs, and how you can intelligently interface this if, for example, things like non-Intel processors, GPUs fly. How can you intelligently interface this to make a more efficient event selection? So we are studying for this, I mean, all these aspects, Ethernet, InfiniBand, advanced network topologies, in particular also flow control stuff. And yes, so that's it.